Good morning, everyone. Welcome back, and thank you for joining us. We're glad that you're here. I'm Steve,
And I'm Scott.
and together we are Backyard Musings, Science and Technology Channel.
Yeah, good morning. And we are talking about a internet topic today, but not necessarily about the internet or um, providing internet service. And I believe you use this internet
I,
service, correct?
I do use Starlink. Yep.
Yeah. So this is Musk's deal, right?
Yep.
He's the guy behind this. So
Yep.
yeah, let's get into it.
Satellites designed to provide internet service are now serving an unexpected second purpose, helping scientists map the nearly invisible atmosphere at the edge of space. Researchers at Kyoto University have used orbital changes from about 1,200 Starlink satellites to map Earth's thermosphere, a thin and difficult to observe region of the upper atmosphere. Their analysis produced the first tomographic map of its kind, revealing atmospheric density patterns roughly 300 miles above Earth. The study was published in Earth, Planets, and Space on July 30th, 2026. Would you like to know more? It's fascinating.
So is this almost like a Google Maps or Google Earth or something like that? Is that kind of what this is, or is it a little different?
No, this is the atmosphere around the Earth.
Okay. All right. Although satellites in low Earth orbit travel through what appears to be empty space, traces of atmosphere remain even hundreds of kilometers above the surface. Collisions with these sparse particles create drag, slowly reducing a spacecraft's speed and altitude. Yeah.
Go ahead.
I was going to say that's what they got to do that's where the main thrust is, right? Is getting out of the atmosphere, getting from land when they launch a rocket or they got to get through the atmosphere. So that's the toughest part. So
that effect becomes more intense when solar activity heats and expands the upper atmosphere. Geomagnetic storms can rapidly increase atmospheric density at satellite altitudes, altering predicted orbits and raising the difficulty of collision avoidance.
Knowing how density varies across the atmosphere is therefore important for tracking satellites, forecasting reentries, planning maneuvers, and estimating the paths of space debris. Yet the region remains difficult to observe directly.
The thermosphere extends from about 100 to 1,000 kilometers, or 62 to 621 kilometers above Earth. More than 99% of the upper atmosphere consists of electrically neutral gas in this region. By comparison, the electrically charged particles of the ionosphere account for less than 1%.
The ionosphere can be studied through its effects on radio signals. Neutral particles in the atmosphere leave a far weaker signal, so scientists often rely on specialized instruments, models, or measurements collected along individual satellite paths. The Kyoto University team instead treated the Starlink constellation as a vast network of moving atmospheric sensors.
Okay. As each satellite traveled through the thermosphere, drag caused it to lose a small amount of orbital energy. The researchers calculated these changes using publicly available detailed orbital records known as ephemeris data. They then applied tomography, a mathematical method also used to reconstruct medical scans, to estimate how atmospheric density varied across different locations.
So easy a child could do it. Yeah. Quote, this is a multidisciplinary study between space science and space engineering. And that's according to the corresponding author, Mamoru Yamamoto. Not making that up, folks. Going on with the quote, reading papers from both research fields, we realize that deeper dialogue between researchers from both fields is necessary. Should that be are necessary? Anyway, this quote.
Combining measurements from hundreds of satellites allowed the researchers to produce a two-dimensional map of density across latitude and longitude. Most earlier spacecraft observations provided readings only along a satellite's individual route, which is similar to learning about a landscape by following a single road.
The new method offers a wider snapshot. Its results were highly consistent with density variations measured by the European Space Agency's swarm satellites, providing an independent check on the reconstruction.
The work expands on an earlier study by the same team that used publicly available two-line element, or TLE, records to examine changes in thermospheric density over time and altitude. The latest research adds the horizontal dimension, revealing how density differs from one geographic region to another.
Future versions of the system could potentially track thermospheric density close to real time. Such maps could improve space weather forecasts, refine orbital predictions, and help operators respond more effectively when solar storms disturb the upper atmosphere. So,
I think
okay.
this is fascinating. Finding out new stuff about the Earth.
Yeah, with an old tool. So that's cool, right?
Yeah.
Don't have to invent something else. Just, yeah, this is cool stuff. Know absolutely nothing about what they're talking about here, but I'm sure somebody out there does, and the people that are involved in this do. So that's the main thing. But yeah, it's cool.
All right, folks. Thanks for joining us. We'll catch you in the afternoon.
Take care, everyone. Thank you.